So this exercise is related to stars in the solar system, and you can also use your mic, chat, or screen annotation to answer the questions. So the first question, which data is needed to calculate the average orbital speed of a satellite around a planet? So if we want the orbital speed, what we have speed is equals to distance divided by time, and orbital speed, it is 2 pi r divided by t. So if we want to calculate the orbital speeds, what are the parameters we need when we compare? So the distance of a satellite from a center of a planet, that we need. For example, if this is a planet and here's a satellite, so we need the distance from the center, which is the radius of the orbit. We need this.
Option B.
The radius of the planet, yeah. So radius of the planet is not, because we don't need for radius of the planet, we don't need the period of a rotation, like the time it takes to complete one rotation, that we need. Sorry, that would we don't need. I mean, the time for a satellite to
Option
orbit the
B.
planet we need. Yeah, option B is the right answer. Is it clear? Because
Yes.
we don't need the radius of the planet, or we don't need how much time the planet will take to rotate. We need the time for the satellite, as well as we need the distance of the satellite from the center. And we use a formula, speed is distance over time, or 2 pi r over t. The next question, approximately how long does it take for the moon to orbit one complete orbit of the Earth? So what is the duration? Is it 24 hour, 1 month, 1 season, 1 year? So 24 hours, that is the time taken by Earth to spin its own axis. That is a 24 hour. 1 season means, because we have like 4 seasons are there, so 1 season refers to 3 months. So 3 months, not the correct one. 1 year means like 365 days. That's the time taken by Earth to move around the star or the sun, you can say. But the time taken by moon to orbit one complete orbit, that is equals to 1 month, or you can say 29 days or 28 days is also acceptable. Is it clear?
Yes, sir.
Yeah.
The next is, the energy generated in a stable star comes from a nuclear reaction. Which type of a reaction occur in the sun? So nuclear reaction or nuclear fusion happen. In a nuclear fusion, the lighter nuclei join to form the heavy.
D.
So helium nuclei break? No. Helium nuclei join? No. It's a hydrogen because sun-like star hydrogen fusion happen. Hydrogen fusion break, nuclei break? No. Hydrogen nuclei join to form helium. That's right. That's why D is the right answer for this. Two quantities defines the Hubble's constant. The speed at which the galaxy is moving away from Earth is v, and the distance of a galaxy is d. What is the relation between vd and what is the current estimation of the Hubble's value? So what is the relation between v and d? According to Hubble's, the further the galaxy, the faster it moves, like greater recession speed. So we can say v is proportional to d. Means those galaxies which are far from us, they're moving much faster. And what is the estimated value of the Hubble's constant? That is 2.2 into 10 to the power minus 18 second inverse. That's a estimated value. So estimated value is 2.2 exponent minus 18, and v is directly proportional to d. So a will be the right answer. So if the galaxy is far from us, it will move much faster. Question 5. Time taken by Mars to orbit the Sun is 690 Earth days. The average orbital radius of the Mars is 2.28 exponent 8 kilometer. An Earth day is equals to 24 hours. Calculate the average orbital speed in kilometer per second. So to get the orbital speed, what is the formula? The orbital speed is 2 pi r divided by t. But the radius, because we want the answer in kilometer per second, so the radius must be in kilometer, which is already there, but time should be in second. What is the time given? It's given 690 Earth days. So first days, I want to convert into hours. So what we'll do, if you want to convert the days into hours, so we multiply by 24. The hours we want to convert into minutes, we'll again multiply by 6, we'll multiply by 60. And then the minutes we want to convert into second, we'll again multiply it by 60. So when we multiply all of this, this will be 5.9 into 10's power 7. So 5.9 into 10's power 7 second. Now we need the orbital speed, so it will be 2. Pi is 3.14. The radius is 2.28 into 10's power 8. We don't have to convert because they already mentioned we need answer in kilometer per second and divided by the time interval, which is 5.9 into 10's power 7. So when we divide, it will be about 24 kilometer per second. Is it clear? This one? How we worked out the orbital
Part B will be oval.
What?
Oval. Next one.
So we call that as an elliptical. State the shape of, because the orbit is not exactly circular, it is elliptical.
Okay.
So don't say oval, it is elliptical actually, like the term which is
Not
used for
eccentric.
the. What?
Eccentric.
Yeah, but you don't use any other term, right? Either ellipse or elliptical.
Okay.
Is it clear?
Yes.
Yes, Hamid.
Sir.
Light from a distant galaxy is redshift. What is meant by the redshift? What is the meaning of a redshift? You have to learn this, the concept of a redshift. What is the meaning of a redshift? That means the wavelength which we receive, it appeared to be longer than what, yeah. The wavelength from a distant galaxy appear to be longer when it is moving away from the Earth. But it's not like you don't say wavelength emitted. If you write wavelength emitted is longer, then it is wrong. You have to say it is emitting out the same wavelength, but because of the motion, it appeared to be longer. So the wavelength from the distant galaxy appear to be longer due to relative motion from Earth as they're moving away, that the wavelength appear to be longer. We call that as a redshift. State the quantity that the redshift of a galaxy is used to calculate. So using a redshift, what we can calculate, remember, we can calculate the speed of the galaxies. So the application of a redshift can also be used to find the speed of the galaxies or speed of the star at which it is moving. So
How?
there is a formula how we can calculate by using a change in the wavelength The red
We
shift,
have
if
to
you
know the
want to
formula.
calculate the, yeah, you don't have to learn that formula. To calculate a red shift, the formula is change in wavelength, but that's not part of the syllabus. How to do this? This is just an extra thing. The formula for red shift is a change in wavelength divided by original wavelength. So when you divide the change in wavelength over original wavelength, you get the red shift or a Doppler shift. And then red shift or a Doppler shift multiplied by the speed of the light, we get the speed of the galaxy. So, but these two formulas you don't have to memorize or learn. As exam point of view, they will only ask what can be calculated, but not how it can be used to calculate. Okay. So only theoretical part is there you have to learn, but not the calculation related to redshift. Figure 10.1 represent different positions A to H of the moon as it rotates around the earth. As you can see, different positions. State a position of the moon where an observer on earth sees there's a quarter of the moon. So where he will observe the quarter, which position? He will observe the quarter of the moon. Because like at this position, we have the first quarter, the cycle of the moon, and this position, we have the third quarter.
Side C.
C will be the new moon, or
Ah, yes.
C will be the new moon. You won't see. Here it will be a full moon. G will be the full moon. The quarters are there at E and A and E, you will observe the quarters. So at this position, so there will be a quarter at position A or at position E. So at position A, the quarter will appear like this. So correct answer for the first one is actually A. And what will happen at E, the quarter will appear like this. But it is acceptable if you write A or E, because it depends on which pole, as it did not specify we are observing from the northern hemisphere or the southern hemisphere. So that's fine. And here we'll have a waxing crescent is there, and then a waning crescent is there. And gibbous, here we'll have a gibbous. Here we'll have a crescent moon. At this position start to be waning gibbous. Then we have a crescent again. How it appear. It's not like the light which is reflected, it's how it appear throughout. So crescent, quarter, gibbous, full moon, gibbous, third quarter or quarter, again a crescent, and then no moon, or you can say a new moon will be there. So the quarter answer is A, but it is acceptable. E is also acceptable. Full moon, where we'll have a full moon, at position G will have a full moon. So you have to practice the cycles of the moon. Okay, the position, according to the position, you should be able to recognize. State the approximate time for the moon to orbit the earth. So you can say take 1 month, acceptable. So 1 month, even 28 days is also acceptable, 29 days acceptable. 1 month, just write 1 month. The average distance of the earth from the sun is 1.5 exponent 8 kilometer. The average orbital speed of Earth. So if we need the orbital speed of the Earth, it is 2 pi r divided by t. We need a kilometer per hour. So it will be 2 multiplied by pi, 3.14 multiplied by radius, which is 1.5 into 10 to the power 8. How much time the Earth take to orbit the sun? Like complete its, if this is a sun, how much time the Earth take to complete its the orbital time? So what is this orbital time? That is actually equals to 1 year or 365 days. So this will be 365 days multiplied by the duration, because we need, like this is days, we want to convert into hours
24.
only. So we multiply by 24. So it is about 110,000 kilometers per hour. That's the speed. It is about 30 kilometer per second or 110 kilometer per hour. That's the orbital speed of the Earth. The speed of a light in a vacuum is 3 exponent 8. Calculate the time for a light to reach the from a sun to reach Earth. So this distance, it is 1.5 into 10 to the power 8. But this is kilometer. We have to convert, we need the time. So speed is distance divided by time. So time is distance divided by speed. The distance is given in kilometer. We have to convert into meters as the speed is in meter per second. So we multiply by 1000. When we multiply by 1000, this will become 1.5 into 10 to the power 11 meter. And the speed is how much? 3 into 10 to the power 8 meter per second. So when you simplify this, this will give us the time it takes. So 1.5 exponent 11 divided by 3 exponent 8, which is about 500 seconds, or we can also say 8.3 minutes or 8 minutes, you can say. So the position, like the light takes about 8 minutes to reach us from the sun. So when we observe the sun, that position is actually the 8.3 minutes before. Next question 7. State the condition required for a protostar to become a stable star. So when the protostar become a stable star, it means the radiation pressure, which is outward, must balance with a gravitational pull, which is inward. So the radiation pressure or inward force and outward forces should be equal, or radiation pressure, which is outward, must balance with the gravitational pull inward. So as a result, the star will not collapse and the size will not change. Define the Hubble's constant. What is the meaning of a Hubble constant? Means H naught. So Hubble constant, because we have the formula V is H naught D. So Hubble constant is V over D. So Hubble constant is actually a ratio between the recession speed of the galaxy and the distance of galaxy. So when we divide the speed, the recession speed and the distance from the observer, what we get the Hubble's constant.
One divided by Hubble constant.
What?
Part B2.
Okay. The equation, yeah, that's right. If we need the age of the universe, we just did that derivation. So age of the universe is 1 over Hubble's constant. And then estimate the age of the universe. So how we can estimate the age of universe in the units second. So what we simply have to do, so time is equals to 1 over the Hubble's constant. So 1 divided by Hubble's constant, which is 2.2 into 10 to the power minus 18. So when we divide, this will give us about 4.5 into 10 to the power 17 second, which is about 13.8 billion years. That is the age of the universe. So these are some questions, like question 1 to question 7 from stars and solar system, other questions as well in this exercise, which I will share with you and I want you to solve. So we discussed the first 7 questions just so you will have an idea how to attempt this exercise. Any question or a doubt related to the session today? Any question or a doubt?
No, sir.